So let's get started. So today we'll have Brendan Bowler, who's faculty at UT Austin. Brendan got his PhD from the University of Hawaii. Had a long named fellowship at Caltech, which is something to do with planetary science, and you know how that ties into astronomy. Very good, but it's very important and prestigious. Then he got a Hubble fellowship to, was that correct? To go to UT Austin?
It was a
McDonald's Hubble fellowship, okay. And then you got hired as faculty member a year or so later. So you've been on faculty for how long?
2 years.
Okay. So he's an expert on exoplanets and imaging exoplanets. So he's going to tell us some exciting news going on that with hopefully a good background in this field, so we can all get up to speed about what's going on here. So thanks.
Yep. So it's great to be here. I'm literally down the road, which I didn't fully appreciate. It's a less than 2-hour drive. And so with respect to the grand state of Texas, we're all neighbors here. So it's nice to come to this institution, which I've also heard a lot about the building, and it lives up to its reputation. We're quite jealous in Austin. We have an old building that is supposed to undergo renovations fairly soon, but I still don't think it'll match up to this. So I'll be telling you about high contrast imaging and what we've been learning about the outskirts of planetary systems via this direct approach to studying planets. I loaded the introduction, packed it more than usual so that we can all make sure we're on the same page. I'm also happy to make this semi-informal, so if you want to ask questions, just raise your hand throughout. So to motivate the field of exoplanets overall, and to remind you about sort of why we care about this, I like to start out with a discussion about the physics that is involved in really what we learn about planet formation, planet migration, the evolution of planetary systems, and then ultimately, I think what a lot of us care about, and which has sort of become the focal point of one of the primary lenses of NASA is habitability. One of the topics that we learn about by assembling statistics of exoplanets and studying their evolution is really understanding how planets form. And some of the key questions are, for example, can planets form through multiple mechanisms? Is there a bottom-up and a top-down approach? There are theoretical reasons to suggest that might be the case, but observationally constraining that is actually quite difficult. Planets evolve over time, they interact with each other, they have non-Keplerian interactions, they also interact with planetesimal belts and migrate in their orbits over time. So we think that these were processes that occurred in our early solar system and helped shape even some of the habitability of life on Earth. We learn about the atmospheres and interior physics of planets by studying direct photons that we can capture and also transmission spectroscopy. The densities of planets from their radii and their masses tell us something about compositions and internal structure. The architecture and context of planetary systems, for example, how common are giant planets relative to smaller planets. This notion of what's emerged over the past few years with respect to the radius distribution of planets was not predicted. This notion that there's a radius gap in the super-Earth regime between the size of Earth and Venus and the size of Neptune. There's a dearth of planets in between those. And ultimately, this notion of habitability of life. How did life originate on Earth? How common are the conditions for habitability? And can we ultimately directly detect evidence of life on other planets via biosignatures and biomarkers? So this talk is going to focus on imaging planets, and to make sure, again, we're all on the same page with this, I wanted to present this sun at 10 parsecs and the difficulty of imaging planets in our solar system at that kind of canonical distance. So there are two regimes to consider. The first is imaging planets in reflected light. And so this is essentially a geometric problem. You have essentially a circle, that is orbiting a star, and you can essentially treat this like a mirror. And so it's going to depend on the orbital properties, the phase, the inclination, the viewing geometry, and also the size of the planet and the distance from that host star. And so this is encapsulated, at longer wavelengths. Then we also have thermal emission, right? Planets have some temperature, they cool off over time. And that temperature is also a function, or the cooling rate is a function of mass as well. So with respect to imaging planets in reflected light, this is a difficult problem because the typical contrast of an Earth-like planet at 1 AU around a star like the Sun has a contrast ratio. So the relative flux ratio is 10 billion to 1. This is the main challenge, and it's, we're talking very close to the star. So 1 parsec, that would be 1 arc seconds, 10 parsecs, 0.1 arc seconds. So this is encapsulated in this equation. So this is essentially the contrast of the planet with respect to the host star. For imaging planets in reflected light in the optical, it's basically a strong function of this reflection ratio. So the ratio of the planet, you increase the planet radius, you're bouncing more light off of it, it's easier to detect. If you bring the planet closer to the star, you're also going to increase the amount of light that's reflected. It's modulated by this phase function, which encapsulates the orbital properties of the planet and the viewing angle. And also the albedo spectrum. So, how reflective is this planet? Is it, are there clouds that reflect a lot of light, or does it absorb like an asteroid? Okay, so when you think of small separations, reflected light in the optical, think about geometry. That's kind of what it boils down to. At longer wavelengths in thermal emission, the contrast is better, because then you're looking at the Rayleigh-Jeans tail of the star, if it's a sun-like star. And you're nearing the peak of the thermal emission from the planet. And so this is essentially temperature. So when you think about imaging planets in thermal emission, think temperature. And it's orders of magnitude easier at longer wavelengths. So right now, this era, we're going to longer wavelengths, and we're searching for massive planets. And so this contrast boils down to, again, it's all about temperature. Also size, but really temperature. So here it's the ratio of the blackbody specific intensities of the sun and the planet, modulated by this radius ratio, which is the radius of the planet over the radius of the star. You can think of that as basically like a luminosity term. So luminosity, this is r squared. You're increasing the radius of the planet, you're producing more light. Okay, so that kind of puts us on the same page. Geometry and temperature, those are the 2 regimes that we're talking about. So giant planets and brown dwarfs cool over time. These are evolutionary models for low mass objects. These are stars here. They contract until they reach the main sequence. Right? The lowest mass stars take hundreds of millions of years to fall onto the main sequence. When the radii contract to that right regime and the internal temperatures are sufficient to sustain nuclear fusion, they'll remain here with a constant luminosity for trillions of years. If they're just below this, then they're brown dwarfs and they cool off over time. They could ignite a little bit of deuterium burning and a little bit of lithium burning for the highest mass brown dwarfs. So you get sort of a stalling of this cooling over time. So these are the brown dwarf curves. They stall and then they continue to plummet. So brown dwarfs also just cool off over time. And giant planets form and cool over time. So these are basically monotonically decreasing curves. Okay, so looking at the census of directly imaged planets, you can see that most planets, right, they kind of span in this logarithmic age range. They kind of span a uniform distribution in age, but in reality, these are all really young systems. Because most of the field stars, right, most stars in the solar neighborhood are very old, several billions of years in age, and so most stars, right, kind of fall in this age bin here, but most of the imaged planets are younger than about a gigayear. And that's intentionally so because these planets cool and fade over time. So if we want to image planets, the easiest thing to do, again, is to go to longer wavelengths, imaging them in thermal emission, and go into younger ages. So what we tend to do is look for the young stars, not knowing if there's a planet there, and then carry out high contrast imaging observations to search for planets. Yeah, question?
I was just going to ask how you're going to
Yeah, so it's all from the stars, yeah. And generally we assume age of planet equals age of star. You can modulate that by a little bit if it takes a few million years to form the planet. But for the most part, on these kind of timescales, it's sort of negligible. So they also transition through these spectral types, right? So we have M dwarfs, L dwarfs, T dwarfs, Y dwarfs, and Jupiter. These look nothing like the stars that you're probably familiar with. The dominant sources of opacity in these atmospheres are produced by overlapping molecular absorption features and dust, especially and clouds for L dwarfs, and then a different kind of cloud starts to emerge in the Y dwarf regime. And so you can see that we get water absorption, which becomes more and more prominent for L dwarfs. The spectrum gets redder, dust condensates can form. We think there's banded structure on these brown dwarfs and giant planets, similar to Jupiter essentially, where we have opacity holes. You can peer down to the hotter, deeper pressures and higher temperatures. As we watch many of these objects, you can see rotational modulations from these inhomogeneous clouds. So there's a lot of evidence for this heterogeneous cloud structure. The temperature range, remember they're passing through all these temperatures, right? So the temperature range typically stands about 2,500 down to about 100 or so Kelvin for Jupiter. And they just continually cool over time. Once you reach T dwarfs, methane absorption, that's sort of the defining spectroscopic sign of a T dwarf, which is methane absorption in the atmospheres. And so in the near-infrared spectra, you get these sort of strong peaky shapes, which are caused by this strong methane absorption. So methane absorbs, and you get flux that can emerge where there's no methane, and so it produces these interesting kind of peaks and valleys. So with direct imaging, we're always battling light from the star. So it's this challenge to remove all the starlight. And so it's easier to image planets at wider separations, harder to image planets at close separations. And so in the phase space of planet mass and separation, direct imaging occupies this regime here. We're sensitive to giant planets at the moment at wide separations. So it depends on how distant your host star is, but for the typical range of distances, maybe 5 to 150 parsecs, and the typical sensitivity, angular sensitivity of 0.1 to a couple arc seconds. This translates into discoveries in this regime, basically beyond 10 AU. And so we complement this sort of outer region, but the goal of the field is not just to find these Jovian mass planets, but to push this down and really explore this landscape here, especially at closer separations. And also to try to recover planets, long period planets, that have been found via other methods like radial velocity technique. Okay, so how do we do this? Let's see, can we dim the lights a little bit more for this slide? Let's hold it. Just turn it off maybe for this one. So there are a few. That looks overly complicated.
I think she was.
Okay, that's good enough. So there are a few observing strategies and algorithms for PSF subtraction that have been developed expressly to get at these deep contrasts at close separation. So just to give you kind of the schematic, what you're going to see here is in the left window, this is the Earth rotating, the star, the night sky undergoing sidereal rotation. What we do at big telescopes, we turn adaptive optics on, and we turn the field rotator off. So if you're any background star or galaxy or whatever, will not remain stationary on the detector. It will rotate about a fixed axis, which is the star that you're looking at. And so if you have a planet or a background star or whatever, that's going to rotate through your point spread function that is created from basically, ideally, this optimal correction from adaptive optics, but in reality, there are quasi-static speckles that come and go on various timescales, and also more or less a fixed diffraction pattern from whatever telescope you're using. So the point is to fix as close as possible that diffraction and speckle pattern on the detector and distinguish that from any real point sources. And usually you can't see the planet, right? In this case, this is a sort of magnified view of that. But then you can see that this real object will have rotated some angle, depending on how long you integrated, what the declination is of your target relative to the latitude of the site. All of this determines sort of how much rotation your object has undergone. So here we started at this angle, and this object moved throughout that PSF pattern by some amount. Okay, here's some actual data. This is going to be a movie on the left. This is from data from Keck with NERC2. Adaptive optics has been turned on. This is sort of a modestly bright star. And what you're going to see is the PSF pattern and speckle pattern more or less remaining stationary, changing a little bit. And you'll see hopefully at least one point source rotating through the image. Okay, so there's the point source. You can see it even in the raw frames. And you can see that that speckle pattern is fairly constant. It's varying, and you have seeing that's changing and AO correction that's trying to compensate for those seeing changes. But it's not perfect. So there are a lot of algorithms that have been developed to optimally, basically to use the science frames to optimally create an empirical template to then subtract off. So this is done in subsections, it's done for the whole image. There's a least squares algorithm that essentially solves for the coefficients, assuming that you can represent a small angular section or a small portion of your image as a linear combination of the other images. And there's also principal component analysis, an algorithm, kind of a whole suite of algorithms that have been developed based on that. And the point is basically to subtract off all this residual starlight. So here's an example using one of those techniques. You can see not only that object that you can see with your naked eye here, but another one here. Rotating
the contrast ratios of those two roughly?
This one here is about 16 magnitudes or so, 16.4, relative to the host
10 to
star.
the 6.5, 10 to the 7.
Ish, yeah. So when you derotate all those frames to a common angle and then add them together, and then align it so north is up here, you get an image like this. So this is that outer object here. This is that closer object that has that contrast of a little over 16. And here's another one. Turns out two of these are background stars. This object is co-moving with the host star. You wouldn't know it from one image. You have to wait 6 months or a year. The star has some proper motion. You go back, you take another observation, and you see if it's co-moving, maybe with a little bit of orbital motion. But you're going to see a lot of images like this. So this is that imperfectly subtracted residual halo from trying to subtract off as best as possible. And all these algorithms are designed to try to get in as close as possible to this host star. These techniques, so that's called angular differential imaging. It's using this, this angular changes of your PSF relative to a real object to subtract off your PSF and add it together. So these techniques and this algorithm in particular have been used in a couple other disciplines, and so this might be of interest to some of you. You can use this, for example, to search for the host galaxies of damped Lyman alpha systems, quasars. You could do this, I've experimented with some colleagues to do this for some asteroids. So in this case, this is a known satellite, known moon to an asteroid. And here we're looking for another object to see if there were two. But you can do this, so this involves non-sidereal tracking, but you're still turning on adaptive optics, and you're essentially using the tools that we've created in the exoplanet imaging community for other science topics. So if you want to talk more about this kind of stuff, I'd be happy to. So that's angular differential imaging. Over the past 5 years or so, a new generation of extreme adaptive optics imaging instruments have come online. These have thousands of actuators. So adaptive optics is this notion where you're deforming a tertiary mirror, pushing and pulling on that reflective surface hundreds of times per second, or thousands of times to correct in real time for atmospheric turbulence. So extreme AO systems, they themselves are adaptive optics units that might be also mounted in tandem with a facility AO system. But the bottom line is that they deliver much better correction. And so these have come online at the VLT, at Gemini, Subaru, and there are some that are coming online that, for example, Magellan, there's a new generation that's coming online, Mageo X, and Keck is undergoing its own improvement on its AO system. And so on the hardware side, there's a lot of developments over the past 10 years. Most of these have come online in the past 5 years, and also on the software side. So it's hard to overstate the importance of software in this field. Okay, so IFUs are great because we can automatically get a spectrum of the planets that we find. So here's an example. This is a 2 Jupiter mass companion orbiting a high mass star at 13 AU. And this is in H-band here. You can see strong water absorption and methane absorption. And so the only window that flux can emerge, at least in this spectral bandpass, is right at about 1.55 to 1.6 microns. So you get this characteristic shape of a T-dwarf. And so from that, we can back up the physical properties and information about the atmosphere of these objects. So this is kind of the haul over the past 15 years or so of directly imaged planets. And every system is sort of interesting in its own way. They're all sort of unique. You have a 4-planet system here. PDS-70, this is a new one that emerged last year, and there's a second companion that is probably a planet, but still not sort of convincing the entire community yet. So a couple, perhaps, multi-planet systems. You have some that are nested within debris disks or protoplanetary disks. Some are really wide separation. So we're starting to fill in this landscape. And the bottom line is when we look at a lot of stars, there are some planets there, right? There's not nothing. And this may be surprising because these are all really massive, right? We're talking 5 to basically 15 Jupiter masses for this population. Okay, so what are we doing down the road in Austin? I've been forming a research group to address a number of these questions related to the atmospheric structure and composition of planets, their formation, architecture, evolution. We're using facilities like Hubble, ALMA, the HET with the new precision RV spectrograph that just came online last year, the Habitable Zone Planet Finder, to address lots of questions related to these topics. So for the rest of this talk, I'll just kind of swing through a few of these. The first is giving you a sense of the demographics that's emerged as a field in direct imaging. So how common are planets at wide separations? What have we learned about their mass distributions and separation distributions? So a bit at the statistical level. I also wanted to talk and tell you a little bit about a new study that we have coming out soon on the population level eccentricity distributions of brown dwarf companions. We're also finding a lot of brown dwarfs, and the giant planets that we found. We can track them over time, and we see a little bit of orbital motion, and we can piece that together and understand their underlying eccentricity distributions as a population. And also about dynamical masses of brown dwarfs and giant planets. So we can actually back out dynamical masses that are independent of models. Typically what we do with direct imaging is we find a planet, we measure its luminosity, we use the age of the host star, and we use cooling models to infer what the mass is. So when I say 5 to 15 Jupiter masses, those are estimates from models. But we're kind of in an era now, and there's a new tool that we can use to measure dynamical masses of these companions, and then actually test the models that way. So the past 15 years, right, we haven't really known where to look. We find nearby young stars, we throw away the binaries so that we're probing a concrete, simple question of what's the occurrence rate, for example, of giant planets around single stars. And we'll use our high contrast imaging software and adaptive optics to go as deep as possible and look for planets. So there are lots of different surveys that have been carried out. These are some of the names. And I'll fill in this table here. So there's sort of a first generation of instrumentation and really a second generation with these extreme AO imagers. Some of these are still ongoing, these programs. To give you a sense of the sample sizes, they started off a few dozen perhaps, up to maybe several hundred. And these aren't all equal. Some go a little bit deeper than others, but to give you sort of a sense of the numbers that we're talking about. There are the large telescopes with adaptive optics, Keck, VLT, Subaru, Gemini. And the first real kind of sizable survey came out a little over a decade ago. So here's another way of looking at that. This is sample size as a function of basically publication year. The blue are for high mass stars. So for adaptive optics, we have better correction with brighter stars. And so surveys, programs have tended to focus on brighter, earlier type stars. And a couple programs focusing on late type stars. And this is filling in the unpublished. So those were the published surveys, here are the unpublished ones. So a few of them are still ongoing. And altogether, there have basically been about 1,000 unique young stars that have been surveyed down to planetary masses with first and second generation instruments. Okay, so the truth of the matter is that there have not been many discoveries relative to the number of stars that we've sampled. So in the direct imaging community, you probably browse AstroPH every day. You see new test planets, new K2 and Kepler systems, and it's this sort of cornucopia of discoveries. And that's serendipitous, in the sense that it was not predicted 20 years ago, and fortuitous. But we're not finding that at wide separations, at least to the limits that we're accessible to and sensitive to at the moment. So I'm going to show you a movie here that kind of characterizes or represents what we've been dealing with in the high contrast imaging community when we carry out a typical survey. So this is basically the first 400 stars. We won't go through all of this, but just to show you kind of what the noise properties look like, what some of the characteristic background galaxies sometimes that emerge, point sources that we find, debris disks that we're seeing. This is sort of what a typical survey looks like. This is from the Gemini Planet Imager survey, the big survey that's been carried out at Gemini South for the past 4 or 5 years. Okay, so, and this is with the Gemini Planet Imager. So you're seeing, this rotation. This is this angular differential imaging. You have a square that's basically rotated. So that kind of maps out the field of view. Every now and again, you'll see kind of a point source pop up there. Sometimes you'll see a debris disk. This is scattered light from a disk around that star. Now, those point sources, the vast majority of them, you have to wait 6 months, maybe a year, go back and image the system. They're all background stars, just boring, anonymous background stars that happen to line up in the field of view. The occurrence rate, it's pretty clear, right, that the occurrence rate of giant planets at wide separations is really low. That's one of the main punchlines that's emerged. We have a lot of non-detections in the field. Now we can still do something with those programs and those statistics. We can take a bunch of observations, find the point sources, wait a little bit of time, take a second epoch, see if it's co-moving. They tend to not be. And the kind of typical rate is maybe 1 planet, maybe 2, per large program like this. And so it's been a little bit disappointing. And this is a hard game, right? If it were easy, it would have already been done. So this is difficult to do. But it's somewhat, I would say, disappointing, kind of the numbers, or the relative numbers that are emerging, relative to planets at small separations. Okay, so we wait, we carry out these common proper motion tests, we can calculate contrast curves. So what would we be sensitive to? We can map those to mass and separation. This is kind of the sensitivity regime for each target. And then amass that into the typical sensitivity of that program. And then start to derive some statistics by drawing boxes and calculating how many we found relative to what we were sensitive to in various boxes in mass and separation. And so this is what's been done. These are the results of occurrence rate calculations for various programs. Here I'm just plotting it up to 2013. And you can see that a lot of these are upper limits. Depending on the evolutionary model you use, there might be sort of 2 upper limits. If they found a planet, this is kind of the 1 sigma and maybe 2 sigma probability distribution function, just kind of marginalized here on this plot. A few years ago, I carried out a meta-analysis as part of a review paper. So if you're interested in a review paper in this field from an observational perspective, I'll highlight this PASP paper from 2016. Basically, I used my own surveys and a bunch of others to amass these unique single systems and use the contrast curves to redo the occurrence rate. And we get something really small, sort of unsurprising, 0.5%, maybe up to 1% or so. The main conclusion is that giant planets either rarely form or migrate to these wide separations that we're sensitive to. I broke this up as a function of stellar host mass. There wasn't any obvious evidence for a correlation with host mass at the time, even though sort of in terms of like case studies, we found more planets around higher mass stars. But at least statistically, using these data, there wasn't any evidence of a correlation. And the bottom line, the punchline really is that we need deeper detection limits, and we need to go to closer inner working angles, smaller separations, where we think most of the power is in this mass and separation distributions. Yes?
Earlier you had said the planets well, that's infrared. These are reflected light, right?
This is all this is all thermal emission.
Thermal
in the infrared,
emission. So
yeah.
you had shown how age dependent. So what sort of age selection is used in these surveys? Is it all everything, or is it just the young?
It's the young stars. So everything from
Wow.
basically 1 million years to a couple hundred. That's kind of the sweet spot.
So you're really pulling out all the stops. You're still not seeing.
Yep.
Wow.
Yeah.
Okay.
Yeah, so they're just not there. And there's been, especially over the past, I would say 2 to 5 years, sort of an existential crisis in the field, right? Careers have been developed, many careers devoted to creating this instrumentation, carrying out these surveys, developing these pipelines, lots of graduate theses, and we're chopping up these planets, dividing the number of planets by the number of people in the field. It's just not a lot. And so we're trying to come up with new strategies, new approaches, and we know that there are planets at kind of modest separations, and so I think that we're at the point where we need to go deeper and we need to go closer in. And that's kind of always been the game, but it's highlighted by these low statistics.
You might touch on this firsthand, but maybe I can say this question. I thought microlensing results were kind of hinting at the opposite results. There was actually large occurrence rates of planets at large separation, but is this just like not large enough separations?
Well, the microlensing results are all for M dwarfs, right? Because statistically it's this chance alignment thing, and most stars are M dwarfs, and so we don't know a lot about the intermediate separation regime from microlensing around sun-like stars, for example.
Okay.
There's an intriguing trend that's emerged now with ALMA disks, right, where there are a lot of gapped disks at separations that were unexpected. So a lot of substructure that high angular resolution imaging in the submillimeter is showing, and that is suggestive if the origin of those gaps are from planetesimals or small low mass planets that are forming. That's kind of a paradigm shift in our understanding of when planets form, how they form, where they form, because we're talking 50 to 200 or 300 AU for many of those gapped disks. And so if those are caused by planets, then I think that there's a lot of potential there if we can just get to lower masses.
How do these ages compared to migration times and the migration? Could it be they formed, but they migrated in before you could find them?
That could be, yeah. So maybe planets form readily at 50 to 100 AU. But as soon as they form, they tidally interact with their disk and in spiral to some small separation. Perhaps that's the case, yeah. But even when we look at young stars with transition disks, for example, or protoplanetary disks where there's some indication of something there, we're still not seeing anything. So it could be they're just below our detection limits. Okay, so when we kind of fill in this occurrence rate diagram with the more recent studies, you can see, especially with these meta-analyses, that occurrence rate is really low. So one punchline to kind of walk away with is that this averaged across all stellar host masses, the occurrence rate is about 1%, assuming one type of evolutionary cooling history, which is called hot start, where you start with a large radius and you simply contract over time. It's possible you can also dissipate some energy via accretion luminosity as gas falls onto your protoplanet, and then you would start off with a lower luminosity. That's called a cold start scenario. That would yield more pessimistic results, probably in this range here. Okay. The occurrence rate is low, but they still are there. And so how do they form, right? Even if it's 1%, that's not nothing. The canonical mode of planet formation is the accumulation of solids in the midplane of protoplanetary disks, which continually increase from essentially dust to dust bunny sizes, up to pebbles, passing the meter barrier to kilometer-sized objects. If you can form cores that are about 10 Earth masses while the gas is present, you can then accrete the gas and form a gas giant. That's kind of the story for giant planet formation that we think holds in most scenarios, and certainly for this, again, this huge cornucopia of objects at small separations. Now, that may actually be enhanced, so you may not have to wait a few million years. There's a new, more efficient method of accretion called Pebble Accretion which has really taken off and has also been sort of a paradigm shift in terms of the locations at which planets may be able to form, maybe much farther out. Maybe it's Pebble Accretion that is producing those planets that we're seeing the signs of with these gapped disks. And also it increases the time scale, so the location and the time scale. So this can happen basically within a year. Another scenario is through disk instability. If massive cold protoplanetary disks can gravitationally fragment and form spiral arms and produce giant planets, then maybe that's what we're seeing. Maybe this population is a representation of this disk instability, gravitational instability mode. They could also be planets that are formed closer in and ejected, dynamically scattered to wide separations. Or alternatively, they could not be really planets as we think of them, but they could be the tail end of binary star formation, in which these planetary mass objects are basically the opacity-limited fragments from cloud fragmentation. So in all these simulations of a cloud forming, you start off with a seed, a really low mass seed of a few Jupiter masses, and you continually accrete. If accretion is somehow halted, or if there's a dynamical interaction with a third body, you can basically stop accretion and halt mass growth in the planetary regime. And so these low mass ratio, these are results from this simulation from Matthew Bate. These very low mass ratio companions that might be what we're seeing. So perhaps it's the tail end of binary or brown dwarf companion formation. So one way to test this is via the eccentricity distributions of directly imaged planets. So all these planets are moving, right? They're not stationary, they're orbiting. And so we go year after year and we continue to take observations, and you can see this nice orbital motion. This is this famous system, HR 8799, which hosts 4 giant planets between 15 and 70 AU. They all seem to be coplanar. We can back out the inclination of each planet. And so that suggests that they formed in a disk, at least for this case study. As an ensemble, we can start to take these companions with a little bit of orbital motion. We can fit Keplerian orbits and back out the posterior distributions on all the orbital elements. Here's an example for one system, GJ504. We have a little bit of change in position angle and a little bit of change maybe in separation over time. We produce a lot of these corner plots, right? And then we can look at the eccentricity distribution. And clearly, for this particular system, high eccentricities are disfavored. So the question here that we asked in this new study is there a difference between the underlying eccentricity distributions of directly imaged planets and brown dwarf companions? And so we've had a Keck AO monitoring program to continue to get astrometry for these objects. Here's just an example for that one object, GJ504. The orange points are the new points, and they kind of line up with existing astrometry. We're doing this for a bunch of systems, getting more and more data, fitting orbits to everything in a uniform way, using the same priors for everything. And we're backing out these eccentricity distributions at the individual level. So this was a fun sort of statistical new tool that we learned. Has anyone used hierarchical Bayesian modeling in any of their work? A few people. So this is a nice framework to either simultaneously back out the individual parameters for individual systems, or do this as well for the population. And so in this case, if you have, for example, a sample of posteriors or probability density functions for a bunch of objects, it might be to measure, for example, some galaxy luminosity function or mass function. And they're different, they're asymmetric, and you want to use all the information in those curves. This approach is pretty straightforward to implement, and it's kind of the right tool for the job.
Excuse me, usually when you use that statistic, you have to have lots of data, because you need to have independent samples in order to do the hierarchy. If you don't have very many objects, I'm confused as how you can use this statistic.
So there's a framework that was developed by David Hogg in 2010 to directly sample from the posteriors in a way that where you build the likelihood function for your population level analysis.
But it's using prior to create posterior. Now you're sampling the posterior to create a prior.
So you use priors at the individual level to then fit the orbits and then back out posteriors for those individual systems. then as an ensemble, as a population, you can use those posteriors that emerged at the individual level to then back out, assuming some shape for the underlying distribution of the population. So that's what we had to assume here. We don't know what it is, so we chose a flexible function in this case, the beta distribution, right? We care about the eccentricity distribution. So the beta distribution is nice because it's shaped by two shape parameters, alpha and beta. You change those and tweak them a bit, and that dramatically changes the shape of this. And so it's very flexible, this function. So we tried this for the full sample. Here's just a plot showing all of the individual posteriors, a constraint on alpha and beta, and then you can see that at least as an ensemble for the full population, there's no obvious preference for high or low eccentricities. It seems like as an ensemble for all the brown dwarfs and all the giant planets, it's basically a flat underlying eccentricity distribution. Yes?
In particle physics, you often assume a logarithmic prior. So you're assuming linear prior, basically. Why linear, why logarithmic? What is, you say it's a general prior, but there is a huge assumption that of the...
We have tried altering the priors, and that doesn't really change the end result.
Logarithmic prior.
We haven't done a logarithmic prior mostly because there's no real expectation. This is not as, it's, we're only spanning 1 decade here, 0 to 1, basically. And so if eccentricity happened to be, this, have a large dynamic range, we would choose some scale invariant prior. And then ultimately you want to change the priors to see if that influences the final result. We've done that a bit, and it doesn't change it. In terms of, it changes the shape a little bit, but not any of the interpretation. Yeah, good question. Okay, we can also break this up with giant planets and brown dwarfs. The giant planets seem to prefer low eccentricities. The brown dwarfs have a much broader underlying eccentricity distribution. And this might change a little bit as some of these don't really add much information, but as we get more and more data, they'll collapse down, and this will presumably collapse down towards something that is more representative of that underlying distribution. But there's no evidence for essentially a strong similarity of the two. They seem to be distinct. So giant planets seem to have more circular orbits.
Actually, I have kind of a dumb question.
Yeah.
In this case, how are you distinguishing between a brown dwarf and a giant planet?
Yes, right. So that is we sweep that under the rug.
Okay.
So we just call it at like 13 or 15 Jupiter masses.
Okay.
There is some evidence when you look at the mass distribution at close separations that the planets, the mass distribution sort of goes down. There's a valley between approximately 10 to 20 Jupiter masses, and then starts rising again when you get to the spectroscopic binaries and the brown dwarfs.
But there's no like spectral signature you're looking at.
No, but that would be super interesting. So we're seeing a distinction between this artificial cutoff of 15. If we had more systems, and eventually when we do, you can start to vary that and see if there's some evidence of a dynamical threshold for this distinction, which would be cool. Okay, so here's another way of viewing it. We can carve it up. This is eccentricity, companion mass, and these are the inferred underlying distributions. We can carve this up in terms of mass ratio, or planet mass, or companion mass, and we're basically getting the distinct distributions, but the inferred, or the interpretation is basically the same. The low mass ratio companions, or the giant planets, prefer low eccentricities relative to the brown dwarfs. And it turns out this brown dwarf distribution and a high mass ratio distribution mimics the binary star eccentricity distribution. So we think that this is pointing towards a common formation route between brown dwarfs, binary stars, and a distinct route relative to this low mass giant planet population. And so altogether, what is emerging in the field is that there's evidence of a bottom-heavy mass function. So when you calculate the relative occurrence rate as a function of mass, this rises up small masses, low masses. We're seeing there's a new paper that came out from the first half of that GPI's survey that is seeing a distinctly higher occurrence rate for giant planets at wide separations around high mass stars. So there's a correlation with stellar host mass. And then the giant planets seem to prefer low eccentricities relative to brown dwarfs. So I think what this is suggesting, it's hard to distinguish between Pebble Accretion and Instability with these particular studies. But at the moment, the trend that's emerging, all signs are kind of pointing to formation within these massive extended disks for the population of planetary mass companions that we're finding. Okay, so I just want to touch on where we go from now in the next few minutes. So we're, again, in this regime where we've been doing these blind surveys. There's a lot of new hardware and instrumentation that will come online over the next few years at these large telescopes with AO improved, extreme AO correction, integral field units, correction into the optical to study things like accreting protoplanets. We can measure rotational velocities for many of these planets by measuring V sin i's projected rotational velocities. We're doing variability studies of these, and when you combine those, you can calculate the angular momentum vector of these planets. We'll pin down the orbits and the eccentricities, and we'll get to even closer companions. And so all this is great, and again, this is a lot of hard work. But I still think that we are limited by this bottleneck of occurrence rate by targeting, in a blind sense, these random nearby young stars. And so I think that what we need to do is transition from these blind surveys to a new strategic direction, focusing on informed targets, where we have dynamical evidence of a planet. Okay, so how do we do that? I think the key, and this is something we've been launching over the past year or so, is to focus on accelerating systems. There's a nice catalog that came out. Some of you might be interested in this. This is a cross-match between Hipparchus and Gaia. It locally corrects for sky-dependent systematics and matches Hipparchus to the Gaia DR2 reference frame. So basically what we're seeing here is three proper motion vectors: an instantaneous vector in the late 80s, early 90s from Hipparchus, an instantaneous vector now with Gaia DR2, and then a joint proper motion measurement between the two. So that's kind of what's in the catalog. So you can use this to test for dynamical evidence of companions. This is for 100,000 stars in Hipparchus. And the nice thing is that this 25-year baseline corresponds to really long orbital periods. So if you see a change in proper motion of a random field star, or hopefully a young star, then that points to something at a modest separation. And the amplitude of that will give some indication of what that mass is. It's not unique, but it'll give you kind of a sense of where to probe. So we've been doing this with a bunch of known systems. So systems with known brown dwarf companions to try this out. This is an example of a dynamical mass we published just using radio velocities from McDonald Observatory and Keck and a few other precision RV spectrographs, and just a little bit of high contrast imaging where we see some orbital motion. You back out a model-independent dynamical mass just from Kepler's laws that kind of looks like this. You know, it's really crummy in the sense that there's a long tail to high masses. We know this thing is not above the deuterium burning or hydrogen burning limit of 75 Jupiter masses or so because it's a T-dwarf. But you know, most of the strength of that posterior is kind of where we expect it to be. Now, just adding the Hipparchus Gaia acceleration collapses this probability density function down to a mass measurement that's better than 5%. So that's pretty great. We've done this for a bunch of other systems. So beta pic B, this is a directly imaged planet. We have a dynamical mass for that. We've done this for other brown dwarfs. We've done this for white dwarfs. So we have dynamical masses for white dwarf companions. And this is working out. Okay, so now we're going to use that. We have initiated sort of a large survey to first vet all thousands. There's about 20,000 accelerating systems. Most of them have high amplitudes, and we want to get rid of those. Those are basically stellar companions, and really focus on the low amplitude accelerating systems. Ultimately, Gaia is going to kind of give us the answer. The sweet spot of Gaia, right? When Gaia releases the final catalog in about, we don't really know when it'll be, 2024 or so, it is going to, the expectation value from known demographics will be tens of thousands of giant planets from the astrometric technique by watching the stars move. So using these Hipparchus Gaia accelerations, using the final Gaia data release, and then using these informed targets from these gapped ALMA disks. So these are high-resolution imaging surveys of nearby star-forming regions. The ones that show potential or maybe promising signs of a giant planet, we can also go after those. So this is where we're headed in the near future. These accelerating systems, gapped disks. And the facilities that we're going to use to carry this out will be James Webb. It will be launched with a series of coronagraphs. Now it's focused on longer wavelengths, and it has kind of a smaller aperture, 6.5 meters. So the combination of those do not get you to a better inner working angle You're not getting to smaller angular separations with high contrast imaging, but you are probing much deeper. We think we'll be able to get down to about a Saturn mass or so with direct imaging. Ultimately, the 30-meter telescopes, right, we're still imaging in thermal emission here. We're going to get to much closer separations, down to a couple AU, maybe 1 AU, and maybe down in thermal imaging to about the mass of Neptune. And then the ultimate transition will be moving from thermal emission to reflected light. And then it's kind of a stepping stone game of decreasing the radius. This will be started essentially with W first, with a technology demonstrator coronagraph to image planets in the optical. And then potentially, ultimately, with a flagship facility like LUVOIR or HABEX. So I'm not going to walk through this, I'm a bit over already, but I encourage you to look at the final STDT reports, which outline sort of this menu of options of both LUVOIR, perhaps with a 15-meter or an 8-meter aperture, or HABEX with a 4-meter aperture. And the ultimate goal, of course, with these is not just to find Earth-like planets, but characterize their atmospheres. So that's one of the focal points of at least 2 of the 4 flagship missions that are being put forward. We outlined some of these topics in a white paper that we submitted. So if you want to read a little bit about what the GMT and the TMT can do together with high contrast imaging, you can look at this. This is with Steph Salem, who's at Santa Cruz, and then a bunch of folks from the direct imaging community. So I'll just end with these points. So the occurrence rate of giant planets at wide separations is low at the moment, but it's bottom heavy. So if we can get to lower masses, then we think there's a lot of promise in terms of finding new systems and being able to characterize the atmospheres of lower mass planets. The eccentricities of giant planets are lower than brown dwarfs. We think that points to different formation routes. We're shifting from blind surveys to informed target selection. I think that's over the next 5 years, you'll see a lot of new results along those lines. And then ultimately transitioning from thermal emission to reflected light is the way forward to get down to those Earth mass planets. Okay, I'll end there. Thanks.
I've been in astronomy a long time. I've never seen a subject where theory has been so wrong as in the field you work in. So